Good day. It is my pleasure having this opportunity to present our research. My name is Hanrui Wang from Monash University. This paper is authored by myself, Xingbo, Zhe Jin, Beng Teoh, and Massimo Tistarelli. This is an outline of my presentation. Let's start from the backgrounds. Cancellable biometrics is developed to raise security and protect the privacy of biometrics. There are 4 properties. Irreversibility means it should be computationally hard to retrieve original biometric features from a single or multiple compromised templates, even under the case where the transformation parameters such as token are known. Hence, the compromise of protected templates will not lead to the privacy invasion. Revocability means it should be feasible to reissue a new protected template when the old one is compromised. Other protected template should remain unchanged when the replacement is carried out. Unlinkability represents it is impossible to perform cross-matching among multiple protected templates across various applications. When one or multiple protected biometric templates have been stolen, the templates that derived from the same identity that is stored in other databases should not be traced. Performance preservation indicates the accuracy performance should not be degraded significantly after transformation. Here I list some notations will be used in this presentation. X and with head are biometric feature vector of original trait and pre-image respectively. R or B is user-specific token. It will be replaced when the user reissues the template. This is very important in our attack. H is protected template. With head means it is for pre-image, and with apostrophe indicates it's for reissuing scenario with different token. In our research, we conducted the experiments under 2 representative cancellable biometric schemes called LM hashing and biohashing. The LM hashing is a ranking-based locality-sensitive hashing method. The LM hashing transforms a biometric template into a set of top-ranked discrete indices of random subspace projection as hash code. Biohashing is binary discretization process to transform biometric feature vector X to a set of binary code. However, existing research has claimed that cancellable biometrics is vulnerable to several attacks, such as ARM, also known correlation attack, or dictionary-based attack, and brute force attack. Our focus in the paper is similarity attack, also known as pre-image attack. Similarity attack exploits the similarity preserving property of cancellable biometrics to generate a pre-image from the protected template. The pre-image is an instance despite not close to the original biometric template. After the transformation, it is highly alike to the targeted protected template. The main contributions of this paper are: first, we propose a constrained optimization-based similarity attack called CSA. Second, we interpret pre-image generation problem from the supervised learning perspective, which justifies why CSA outperforms GASA significantly. GASA is the method we derived our CSA from, but without constrained optimization. Third, we conduct experiments to demonstrate the CSA against LM hashing and biohashing with LFW face dataset. We revealed the hardcode size is one of the key factors to impact the attack performance. Next, I'm going to introduce the method of CSA. CSA is still similarity attack, so it follows the basic concept of the attack. The ultimate aim of a similarity attack is to generate a pre-image X head, which is close to original biometric feature vector X. However, in cancellable biometric system, X is discarded after transformation. The transformed templates Y are stored in order to preserve accuracy. The relative distance between Y and Y head are to be preserved. The problem can be reformulated to minimize distance of protected templates. So we define the loss function by the distance of protected templates. Here is a sample using notation of LM hashing. As I said, we interpret this problem as supervised learning because in similarity attack, the token used in searching pre-image is unchanged, but X is changing. We consider the token and the protected templates are paired X and Y as training data, just like a feature vector paired label. In terms of its transformation algorithm, we can consider X and Y have both L dimensions, so we can consider the size of training data is L. As we have known in supervised learning, to obtain a good verification performance, we expect a low loss value in training and low overfitting rate. We adopted the same way to improve the attack performance. First, I need to introduce some definitions. Test error is defined by the distance of protected templates of original biometrics and the pre-image after we reissue the token. This is the main case we care about as we aim to develop an attack to generate a pre-image still works after reissuing the templates. Training error is defined by the distance of protected templates before we reissue the token. This is the loss value in training. Variance indicates the overfitting grade, so we use the differences of training and test error. N here is verification times as we run the test for 10 times to increase the generalization. As we mentioned the factors of good performance of supervised learning, in our attack, we minimize training error with constraints. We make it to 0 and alleviate overfitting with larger hashcode size. Recall the hashcode size is considered as the size of training data. This is the result to prove our theory. It is clear that with constraint training error, the blue line remains at the best level, it is 0. Although the variance, the yellow line is higher than GASA, but with larger hashcode size, it reduces significantly. The test error of CSA is finally much lower than GASA under large hashcode size. In this slide, this is how we establish inequality constraint of LM hashing. Inspired by the ranking property, we identified the Z with index value equals H is the maximum value in the vector. So we built the inequalities by this reason. For different cancellable biometric schemes, such as bell hashing, we need to identify different constraints respectively. At last, we use ALGA to search the pre-image. The original GA is an unconstrained optimization problem, which is kind of ad hoc. ALGA is optimized for constrained searching tasks. It's an iterative 4-step procedure. Other than ALGA, there are more optimization methods where the constraints can be applied. In this work, we are more interested in the constraint optimization than the searching algorithm. So ALGA is only the choice of the implementation. Next, I will illustrate our attack performance. First, we select the partial data in LFW face dataset. We select the subjects with more than 10 images and choose the first 10 images of each subject. All the selected images are extracted to 512-dimension feature vectors by inside face. Our attack scenario is as displayed. First, we generate the pre-image with the first face image of each subject, assuming the users enroll the system with the first image. Second, after we obtain the pre-image, we reissue the template. Assuming the system is compromised and the user reissue the templates. Last, we generate the protected template with pre-image and the new token. Then access system, verify whether our pre-image is available to breach the system and the new token. This matching is conducted using left 9 face images of each subject. And here are our test results. Look at the bold number. Our proposed attack obtained over 99% successful attack rate with 512 hardcode size and 30% better than GASA, which is without constraint optimization. This proves the effectiveness of our method and indicates that the better recognition rate leads to more security risks. For biohashing, we get the same conclusion. CSA performs much better than attack without constraints. However, the CSA model suffers from three limitations. First, the CSA relies on information leakage restrictively. This means it requires the knowledge of the protected template, transformation algorithm, and its associated parameters. Secondly, unlike GASA, which requires no constraints, CSA expects constraints to be established, which could be difficult for some cancellable biometric schemes, such as Bloom filter. Finally, the generated pre-image is not available to reconstruct the face images. In future developments of this research, the generalization of the CSA model against the other cancellable biometric schemes will be addressed. Moreover, countermeasures such as adopting nonlinear transformation or integrating permutations before applying the transformation to enhance the security of cancellable biometrics against the attacks, including similarity attacks, will be investigated. And if you are looking forward to a deeper discussion or any cooperation, you can contact us with email. At last, we appreciate a lot for the support of these departments and corporations. Here are some references in these slides. This is the end of my presentation. Now I leave the time to the questions. Thank you.